Welcome back to part 2 of my math and physics books collection. In this section, as promised, I'm going to cover the physics section. So just like before, this will be split into 10 subsections. Starting at number 1, we have conceptual overviews and mathematical methods. Number 2, we have classical mechanics and undergraduate general physics. Number 3, we have quantum mechanics and mathematical quantum theory. Number 4, we have Lagrangian and Hamiltonian dynamics. Number 5, we have classical field theory, electromagnetism, and special relativity. Number 6, we have statistical mechanics and thermodynamics. Number 7, we have astrophysics, general relativity, and advanced classical field theory. Number 8, we have quantum field theory and mathematical gauge theory. Number 9, we have nuclear physics and particle accelerator physics. And then we'll finish off with number 10, quantum gravity, classical and quantum cosmology, and unified field theory. Let's begin. For our conceptual overviews, this is a 2-volume book by Stephen Hawking. This is the illustrated A Brief History of Time and the illustrated The Universe in a Nutshell. This doesn't get into the mathematics, but it's a good introduction to the world of physics. If you want to get deeper into the mathematics and to get a general overview of physics as a whole, this is probably one of the best books ever written. This takes you from the very basics of what it even means and the ancient idea of having a number all the way to, canonical quantum gravity, Penrose's twistor theory that he's introduced, M theory, and everything in between. This was shown in the last video, but I'm showing it again because it's good to get a review of all these basic elementary introductions to all these fields of higher mathematics before going into physics, of course. Starting out, we have Leonard Susskind's Classical Mechanics, the Theoretical Minimum. So this is not going to be your most rigorous overview of physics, but it'll be a pretty decent introduction to it. And this goes into certain things like the Euler-Lagrange equation, which you may not get into until you get pretty far into basic physics, especially at the undergraduate level. To get a more rigorous undergraduate overview of physics, I recommend these 3 textbooks by OpenStax Project. This will take you over Newtonian mechanics and then give you introductory quantum theory. It'll give you a decent overview of electromagnetism, optics, wave mechanics, and then a little bit of stuff regarding relativity, condensed matter physics, nuclear physics. It doesn't get real heavy into those higher physics fields, but it's perfect for an undergraduate overview of all the main courses of physics. So we have Leonard Susskind's Quantum Mechanics, the Theoretical Minimum, to start off our quantum mechanics journey. This goes a little bit deeper into the theory than the university physics course, but it's not as rigorous as the overall course. So this will just be a good introduction into quantum theory. This would be what I would consider a more proper introduction to quantum theory, and this is a legendary textbook by Griffiths and Schroeder. So yeah, if you're more serious about getting into quantum theory, this would probably be a good place to start. If you're looking for that mathematical rigor, though, this is the best book ever written on the topic. So it gives you the basic mathematics of quantum theory, your position, momentum operators, gives you the Heisenberg picture, the whole idea of waves. It starts off even with a review of classical mechanics, and it does a really good job of that. But later on, this goes further beyond things like the uncertainty principles, and it goes into things like Segal-Bargmann space, quantization of Euclidean space, Lie groups and Lie algebras, tensor product representations, the Feynman's path integral, Feynman-Kac formula, Hamiltonian mechanics on manifolds, geometric quantization. This gets into connections, polarizations, line bundles, half forms, and pairing maps. So yeah, this one gets pretty advanced. And if you're looking to get really advanced with the theory, this is probably a good introductory book on the more advanced foundational quantum theory. This will cover a couple of aspects of quantum field theory as well as it gets further into it. So yeah, I would say this is probably the most intense book I have on foundational quantum theory. In this category, we have one book because it deserves an entire category to itself. This is Mann's Lagrangian and Hamiltonian Dynamics, one of my favorite textbooks ever written. Pretty interesting, because though this is designed for an undergraduate physics course, you could definitely put this into a graduate level hands and have people learn something from it. So you go over things you would expect, your boundary conditions, your variations, and all your principles, and then your Hamiltonians, your Lagrangians, the Euler-Lagrange equations, Hamilton's equations in principle, your Poisson brackets. But then you go into classical propagators, Koopman-von Neumann theory, symplectic integrators, Poisson manifold theory, canonical perturbation theory. It goes further into Noether's theorem for fields and finishes off with an overview of classical path integrals, something you definitely don't get at an undergraduate level typically when it comes to classical fields especially. So starting this off, the book I learned this from first before I got into any others, we have Leonard Susskind's Special Relativity and Classical Field Theory in the Theoretical Minimum series. Always a good idea to have this in your collection. Surprisingly enough, this gets into things like the Klein-Gordon equation after it covers basic things of special relativity. It gets into Euler-Lagrange field equations. It gets into Maxwell's equations. It goes into Poynting vectors, Noetherian momentum, field Hamiltonians, and even finishes off with the electromagnetic energy momentum tensor. So I thought this was pretty interesting for the level it's intended for. No Nonsense Electrodynamics. The No Nonsense series is good in general. I have another one on quantum field theory you're going to see here soon, so I recommend this one as well. This is good for a simple and advanced introduction to electrodynamics, whether you want to see it from the basics and how it relates to special relativity, or if you're more interested in the tensor form of electrodynamics. So yeah, you're going to get Maxwell's equations, Maxwell's Lagrangian, and then you're going to get an overview of the Dirac delta distributions, the Kronecker delta function, and all of these sorts of things at the end too, for those that need those reviews. If you want a more rigorous and graduate level overview of electromagnetism, Garg's Classical Electromagnetism in a Nutshell is top tier. So yeah, this is a much more advanced textbook on E&M. So you're going to get electrostatics and magnetostatics and electrodynamics and magnetodynamics, and then their combined dynamics in their own separate fields of study here combined into this book. So you're going to see how they work in mediums, how they work in the vacuum, and then their applications therein. So yeah, you're going to understand things like frequency-dependent responsive materials, insulators and conductors, and how they work with electromagnetic waves, electromagnetic radiation scattering. You're going to learn about Thomas precession and synchrotron radiation. Pretty interesting things here. This is a classic textbook on statistical mechanics. And in fact, it's actually known entirely for its second part that covers quantum theory from the ground up. And so this would actually be a good addition for those that are just interested in quantum theory, although it covers other things as well. So you're going to learn even things like Einstein-Bose distributions, Fermi-Dirac distributions. These are part of the spin statistics theorem. You're going to learn about the gases that come from these systems, the different H theorems, whether they be classical or quantum mechanical. It's going to finish off with things like grand canonical ensembles, the Gibbs paradox, and thermodynamic equilibrium fluctuations. Here we have general and statistical thermodynamics. This is a Springer Graduate Series textbook on the topic. So these two books are good to have in conjunction with one another. This one will go further into things such as those spin statistics theorem results in Fermi-Dirac statistics and Bose-Einstein statistics as well. And it'll go into things like Landau theory, Cooper pairs, quasi-particles, superconductivity, and things of that nature. And that's, of course, after covering the basic theory of thermodynamics prior. Starting it off, one of the best astrophysics books, An Introduction to Modern Astrophysics by Carroll and Ostley. So you're going to learn all about the cosmos, both local and universal, essentially, in this book. But it doesn't go deep into general relativity, so those with the basic understanding of calculus can get through this book pretty far. And it covers a lot of critical information. Really interesting book to read in general. And then we have Soshi's introductory textbook on general relativity. So, not your most rigorous introduction to the topic, but it's a good overview for those that want to see its applications to differential geometry and physics. But if you're wanting a serious coverage of general relativity, of course we have to go with the Bible of general relativity itself. This is Misner, Thorne, and Wheeler's Gravitation. So an undergraduate could come into this, or someone who's interested in self-study, and start gaining some knowledge from this book out the gate. But those that want a serious postgraduate research level understanding of general relativity, they can go into this book, despite it being written originally in the 1970s, and still start contributing to the field. I mean, this book really takes you deep into the theory and starts touching on pioneers, like pioneering areas of the field that we're still trying to wrap our heads around. Of course, Kip Thorne, one of the authors of this book, worked on the mathematics for the movie Interstellar. He's the one that created actually helped model the black hole in the movie and gave some advice on other parts of the movie as well. And he also contributed to predictions of gravitational wave, astronomy, and ways that we can go about detecting these gravitational waves. And this book gave a couple of those predictions. Of course, they're accurate. And in 2017, Kip Thorne won the Nobel Prize for this dynamic prediction. If you want to go further into the study of black holes and astrophysics, this book by Meyer in the Springer Praxis series is, bar none, one of the best books you can find on black holes. So yeah, you want to go all the way into relativistic gravito-electromagneto-hydrodynamics. This is your book. This will take you all the way from just what it means for a black hole to maybe exist out there to, oh yeah, we've discovered these things, here's how we know they exist, to their mathematics all the way up to the tensor calculus and differential geometric level. So this assumes you know general relativity and builds upon that. Takes in all the other fields of mathematics and kind of mixes it together. And so you learn about Comptonization, nucleosynthesis, accretion disk in black holes, magnetohydrodynamic jets. You learn about neutron stars as well, and the different sizes of black holes, such as stellar mass, intermediate mass, massive, and supermassive black holes. Then we have O'Neill's The Geometry of Kerr Black Holes, a book that's good for the study of differential geometry as a whole. And of course, the Kerr metric describes most black holes in our universe at a geometric level. So this is an interesting book to study because it turns out black holes have crazy properties at the mathematical level. And this book gives you a preview of what that might be like. And then we have classical field theory. This is an advanced textbook on research level classical field theory, preparing researchers and students for not just quantum field theory, but for further study in advanced classical field theory for problems that we're still solving in it to this day. So this one's pretty interesting. This covers more than just the typical classical field theory you would expect in an undergraduate level. In undergraduate level courses, for example. So, you think of electromagnetism, you think of special relativity and its applications in electromagnetism, you think of general relativity at a higher level. But this one goes further than that. This goes into Procca fields. This goes further into the Poincare group as an extension to the Lorentzian group. So instead of just SO13, you have ISO13, and this kind of extends that to say, hey, we're focusing on greater symmetries here. We're focusing on gauge theory and what that means. So you go into Maxwell dualities, Hopf maps, complex scalar fields in this case, the abelian Higgs systems. They go over Chern-Simons fields, the Dirac equation, the Einstein-Hilbert action. This goes further into anti-de Sitter space, the Gibbons-Hawking multi-instanton solution. You name it, it's all here. This is really interesting stuff, especially for classical field theory. There's too much to name here, so I'm going to stop there. So Schmidt's Particles, Fields, and Forces, A Conceptual Guide to Quantum Field Theory and the Standard Model, is a non-mathematical book that introduces you to not only quantum field theory, but introductory quantum theory as well from a non-mathematical level. So this could have been included in the first section of this video in the conceptual part. But even for something that's non-mathematical, this covers a very advanced topic, so I just throw it into the quantum field theory section because that is what it covers. So yeah, you're going to understand what Feynman diagrams are, what a U1 gauge field, SU2 gauge field, and SU3 gauge field is, but just without all the mathematics essentially. And then we have another one from the No Nonsense series, Quantum Field Theory. This is probably the best introductory textbook on quantum field theory because it gives you the simplest introduction to it. And yes, this one goes straight into the mathematics. So you're going to actually learn quantum field theory from this book. But if you're really serious about learning it, I recommend these two volumes. A Modern Course in Quantum Field Theory, Volume 1 Fundamentals, and Volume 2 Advanced Topics. So this will take you all the way up to the construction of the Standard Model Lagrangian and then beyond, including conformal field theory, the ADS-CFT correspondence, the CFT black hole correspondence, modular Hamiltonians, and onwards. So you're going to get all your quantum electrodynamics, your quantum chromodynamics, and your electroweak theory all covered together before it's all summed together into something greater. And I showed this book in the mathematics section video, but I covered the pure mathematics centric area of the book and said, hey, it covered aspects of quantum field theory and the Standard Model. In this video, I'm just going to list the things it covers regarding the Standard Model itself. So yes, it provides a construction of the Standard Model Lagrangian, and it kind of fills in that space a little bit more so than even the last book did. Yeah, this is an absolutely wonderful book for both pure mathematicians and physicists. So we have Sagawa and Albertelli's Modern Nuclear Physics. So I say if you have a good foundation of quantum field theory before going into things like modern nuclear physics and particle accelerator physics, you'll be able to go further into it than most people that are just going headfirst into these types of studies. We have Particle Accelerator Physics from Springer's Graduate Text Series. This one's very interesting because it tells you all the components of the actual accelerators. There are different types such as linear accelerators, betatrons, microtrons, cyclotrons, synchrotrons, isochron cyclotrons, and synchrotron accelerators. All the different things that are involved in the particle beam dynamics, the Fokker-Planck relation, or equation rather, Cherenkov radiation, free electron lasers, Hamiltonian nonlinear beam dynamics and perturbation theory, Compton radiation. It's all included here. Very interesting book. Very large one too. It's over 1,000 pages of this. Very mathematically dense too, of course. We have Vissar's Lorentzian wormholes from Einstein to Hawking. This is a mathematical physics textbook on modern wormhole theory. So this starts off with overviews of basically the conjectures regarding black hole theory, such as Hawking's chronology protection conjecture, Novikov's consistency conjecture, the radical rewrite conjecture. And then it goes into things like reminding you of things about general relativity, such as Lorentzian spacetime, Christoffel symbols, the geodesic equation, the curvature tensors, the energy momentum tensor, and it actually shows you how that's derived from the Einstein-Hilbert action. This one goes into the comparison of linearized gravity versus strong gravitational fields. It goes into the different types of horizons that exist before hitting Schwarzschild, Reisner-Nordstrom, and Kerr-Newman geometry. It goes into Wheeler wormholes, traversable wormholes, and Morris-Thorne metrics, the Casimir effect, and all the quantum effects that get involved in traversable wormholes. It goes into wormhole spacetimes, Jacobi tensors, Weyl tensors, these cubic and polyhedral and dihedral wormholes, and it keeps going. I mean, from non-Hausdorff manifolds, and then finally ends with mini superspace wormholes. So, again, it's more than I can actually ever hope to mention, but if you want a complete textbook on wormhole theory at a mathematical level, This is as close as you're going to get to it right here. Then we have Wald's quantum field theory and curved spacetime and black hole thermodynamics. So yeah, it gives a good review of Hamiltonians in phase space and a review of quantum theory as well as quantum field theory in flat spacetime, and how the idea that particles are an inevitable conclusion of something that's going to occur if you have a quantum field theory. It just gives you the inevitability of particles in a universe modeled by quantum fields. And then it goes into the Klein-Gordon field in curved spacetime and the Klein-Gordon equation for curved spacetime, before hitting your Weyl C-star algebras, the Unruh effect in flat and curved spacetime. It goes into Hawking temperature and Hawking radiation, and the laws of black hole thermodynamics and black hole evaporation as a whole. Very interesting book. Pretty short read too. It's actually not that long, but it is a fairly advanced read. We have Calcagni's Classical and Quantum Cosmology. This goes over the many different types of cosmologies, from loop quantum gravity to M theory to causal dynamical triangulation, group field theory, spin foam theory, non-local gravity, asymptotic safety, causal sets, non-commutative spacetimes, Wheeler-DeWitt cosmology, which is sort of a canonical cosmology in a sense. And you go into dilaton, cyclic, aperiodic universe models, de Sitter and anti-de Sitter vacua, and all of these interesting things that are involved in the modern study of classical and quantum cosmology. Then you have a similar book on quantum gravity and quantum cosmology. It's a similar book, but it goes into a slightly different direction. It gives you an overview of many of the things that I mentioned in the last book, but this also gives you an overview of things like dark matter and dark energy as well, as far as observational overviews and their theoretical models. It goes into inflationary cosmology, further into matter balance and quantum gravitational effects on primordial inflation. Then we have Rovelli's book on covariant loop quantum gravity. This is probably one of the most complete and best textbooks on modern loop quantum gravity that's out there right now. Now, I'm not the type of person that thinks that, for example, loop quantum gravity is the theory of quantum gravity. I don't necessarily think that. I believe that these all have mathematical relevance that can extend to multiple fields of physics and other fields of science. And that leaves us with the final book. Becker, and Schwartz, String Theory and M Theory. So yeah, very advanced textbook here. Starting off with things like the Virasoro algebra, when it starts off with bosonic string theory, it goes into Kac-Moody algebras, and then it goes into your supersymmetry, super string theories as well from the supersymmetries. And then it goes into your S dualities, T dualities, the M theory that corroborates all these different types of M theories. This covers a bit of a K theory, Calabi-Yau manifolds and their compactification, Sasaki-Einstein space, holonomic manifolds, Bekenstein-Hawking entropy, and all kinds of things. How it relates to black holes, such as the ADS, CFT, correspondence, and holographic duality. And general overviews of applications within conformal field theory. But that's all for this video. If you're interested in any specific reviews of any of these books, feel free to let me know in the comments below. Thanks for watching.